Okay, now we are recording the class. I'd like to thank you again, Guilherme Avansi, for giving this seminar. I was explaining that he's trying to show how to use the data that Manuel told you last week, how to put this into a reservoir simulation, how to build these models. And after test one, we're gonna check also some details about these models. Guilherme Avansi will talk today more about how to use them and what's inside, how we're gonna select these models and so on, okay? And thank you, Guilherme Avansi, for that. And once again, if you want to make any questions, you can make in Portuguese or in English. You're feel free to interrupt at any time, okay? Thank you, Avansi.
Thank you, Professor Nis. Thank you for this invitation. It's always a pleasure to be here to present what I'm doing here for the last period of time. I think this might be 5, 6 years. So thank you so much. So the idea to present today is, as Professor Dan said, to talk about a little bit how we to build the simulation models and how we can use this type of fidelity when you have a different type of application. If you have time, I will talk a little bit about the type of model that not include the physics. What it means physics is the flow in porous media. That is kind of analytical formulations, such as proxies, emulators, and so on. So if we have time, I will discuss this with you guys, okay? So let's start. So this is the third class that talk about simulation model of different fidelities. And simulation models is a broad topic that we will discuss by talk. So let's see where we are here. So if you can see here, we have this workflow that is the common workflow that our group is using. So Manuel talking about the different, how to use this geological model, how to build this geological model that we call here high fidelity models. So I'm here in the fit for purpose models. So with this idea, we have different type of objective. If we work for the future, is the blue area, and we work for the past. This is what's previously presented by Professor Dennis in the first class. So I will not give details, but I would like to highlight where we are, okay? So this is the 12 step that Professor Dennis also present. So we are here. The step 2, that is the model construction. So this model construction, what it means model construction? So we need to build consistent, efficient models. Remember, when we are talking about model construction, I'm looking for the fit for purpose models. So with this fit for purpose models, we need to understand what is the main objective that we want to have as a target. So we have here reservoir simulation models, we have proxies, we have emulators, and other tools that we can use as a model. So with these models, petroleum companies can decide what is the most suitable model to be used based on importance of study, because, for example, we have 3 different type of applications. I will explain this in the next slide. So we have, the first one is uncertain reduction that we are calling here data simulation for uncertain reduction. And the other is linked to the future. That is production forecasts and decision analysis. So this is the importance of the study. The available time, why it means available time? Because sometimes we have a manager, the manager is asking, oh, I need this for yesterday. So we need to speed up all the analysis in order to give the best result as we can with the available time. So the time that he asked for, right? And also the resource. Sometimes we don't have kind of cluster or a powerful machine. So we need to take attention to this, because sometimes we don't have enough resources to run thousands of simulation models. So this is the important one. So we have a kind of balance that we have the objective of the study, the available time, and also resources. So when we build consistent and efficient models, we have 3 main areas that we can use. The first area is relate to the past, as I already presented. This is the data simulation for uncertainty reduction. The second one is the future. So you have production forecast and decision analysis. Based on this, you can now we know where we are. So let's go to the next slide. That is the outlining of this class today. So the outline is I will present the simulation models, more relates to how we build the simulation models. I will present a little bit about complexities and also model validations. We have also the second part, if we have time, we explore this, that is about the proxies and emulators. And I will give a general idea of what does proxies means and also emulators, because emulators, if we are talking about Bayesian emulators, so it's a little bit different that we use in the whole area when we use proxies, right? And also the part 3 is kind of models and proxies. Models means the different type of fidelity and etc. And the final remarks. So let's start talking about how we build these reservoir simulation models. So this is the next step. So we are here, Manuel also presented last class about reservoir characterization. Now we'll go to the next step, that is the model constructions. So what is the problem that we have to build the proxy model? We have a lot of information that we need to include in these simulation models. What we have? First of all, we need to have a grid. What means grid? We need to have the limit of the reservoir that is linked to the top and base, and also the limits that may sometimes we have faults kind of separate these reservoir simulation models. So we have information from the reservoir, for example, oil water contact. If we have an aquifer, if this aquifer is active or non-active, or is a little bit. So we have rock properties, because remember, when Manuel presented reservoir characterization, he presents a different type of rock properties. What it means rock properties? Now we can talk about here phases. So we have this kind of phases here. We need to relate for each type of rocks that we have in our model. We need to include these curves, right? So the fluid properties. The fluid properties is very important, because with the fluid properties we can have an idea how is the relation when we are talking about pressure, volume, and temperature. How is the pattern of this fluid when we have different pressure, temperature, and also volume inside a block. Just to remember, we build this grid, and this grid has several cells, several grid blocks. So with this information here, I also present is the limit. We have the different top when we have inside the reservoir, different faults here. You can see the internal faults and also the limits. So with this, we can relate to the core analysis, that is more relates to where you have reservoir porosity and also permeability. And sometimes we have this seismic. Can be a 3D. With this 3D, we can map the faults, or also for this seismic.
Guilherme?
Sorry, yeah.
Guilherme, o som, está me ouvindo?
Yeah.
O som aqui está falhando bastante, não sei se é só para mim ou para os alunos também, se puderem falar aí, só para eu verificar. Daniel está aí, você está ouvindo bem?
Ele está falhando também para mim. Está falhando bastante também.
Professor, if you can give me a minute, I can try to rebuild the internet here, because I already tried this morning. So
now it's okay. If you can follow, I can just repeat the last slide, and then we can follow. And if it's failing again, then I can tell you.
Yeah, because I also reset the internet before I started this meeting. So let's see. Yeah. Okay. So so what's the problem that we have here? So just to remember, we are in this step, the model construction. So when we are in the model construction, we have a problem. What the problem that we have here? We have several information that we must include in our reservoir simulation model. So we have here this grid, that is a spatial grid that we need to build in order to include all information that you have in each block here, right? Sometimes you have an aquifer or a gas cap, right? We need to map this oil water contact, and we need to identify if this aquifer is active or non-active, right? We have also the rock properties. Sometimes, as Manuel presented in the reservoir characterization, we have a different type of rocks. So when we have different types of rocks, we need to correlate this information with different type of curves that is more linked with the water relative permeability and also the water permeability curves. And we have the third phase, that is gas. We have also for the gas. So this is the relationship when we have the permeability relative curves linked with the water saturation. And also when we have the fluid properties here. And we are talking about the fluid property, what it means. I'm talking the relationship among, right, the pressure, the volume, and also the temperature. And we need to understand this behavior when we are in different depth that's related to the pressure and also the volume. Just to remember, when we are building these grid cell here, we have a volume by each block or grid block, right? And also we have the geologic description. The geologic description means we have the top, we have the base, we have the limits, we have the faults here. We can see the internal faults of this model, and also the information that we have from the blocks here, right? And also when we have, for example, we have a 3D siding. The 3D siding is used to get the information from the faults, and also the 4D siding more relates to the fluid movement. So we also can include this information in our simulation model here that we have. We have also the position of the wells, where the well is perforated, right? We have the well in facilities. We need to include this information of facilities. So I think we have one presentation about talking about how to link the reservoir with the facilities that we have, and also the production curves. Because sometimes we have a period of history, so we need to include the information in the reservoir simulation model. So this is the information that we have. We have a lot of information that we need to include. So this is the goal. We need to be careful when we build a reservoir simulation model. It's not just to include information, that's it. So I will try to pass step by step, right? So here, as we can see here, we have this information from a reservoir, for example. We have the resolution here is 30 meters, right? So when we build our grid, simulation grid, just to remember, we have the information here for 30 meters, and we build in a grid cell of 100 meters. So for each grid cell here, or grid blocks, we have information of porosity, variability, and etc. And this porosity variability is linked directly with the type of reservoir rocks that we have. So we have different distribution for different type of rocks. So this is a general workflow that we use to build our geological model. So we have the pre-processing data from geological and geophysics data interpretation. So Manuel explain or give all this information about this pre-processing data with this show model here. And also we post-process this geological model in order to build our numerical simulation model here. So when we are talking about this pre-processing, we are talking about structural modeling. Structural modeling is the limits of the reservoir, top, base, and also the grid that we create for geological model. We have the attributes assigned in wells, well logs, for example. We need to, in these well logs, what we need? We have different type of resolution. We need to fit this resolution here from well logs into our grid simulation, right? And also the petrophysics and core. So the petrophysics and core is also analysis of this pre-processing geological and geophysical data. So when we have all the information here, we can build our geological model here, build our geological grid, and simulating the phases, simulating the reservoir properties. What I mean, porosity, permeability, and sometimes water saturation, etc. So this is the step of reservoir characterization. Reservoir characterization. So this was already presented by someone, by Manuel. So when you are moving to the next step, that is the model construction, we need to post-process this analysis. What I mean is post-processing. We need to create a numeric simulation grid, because we remember when we build our geological model, this is a high level grid resolution here. So it's impossible to simulate this geological model. We can simulate, but just a few simulation, just a few executions runs, right? So it's not possible to run thousands of simulations here. So we needed to create a new grid that we call this grid as a simulation grid. So with this grid, we need to include all the information that we create for the geological model into a different grid. Sometimes we use the technique that we are calling about the upscaling techniques, and sometimes we can model there directly into the simulation grid. So we need to be careful, because when we simulate directly in the simulation grid, we are avoiding to model everything in the geo model. This sometimes is good because we can map all the heterogeneities that we have in the reservoir. So sometimes it's good, sometimes not. Sometimes we need to have a balance. So what is the most important? To get all these features, these heterogeneity in the simulation model or not. So we need to be careful with this type here. But is the traditional is to build a simulation grid and then perform all the upscaling from all the probes that we have, including also the upscaling from the structure model. Because we have a different structure model here, we need to upscale this structure model in the reservoir simulation grid. And then finally, we build our simulation model. We have all the information from the structural information, the grid simulation, and also everything that we relate to porosity, permeability, and so on. So we have this model constructed. So let's move by step. I just will pass all this step here, but just to remember what Manuel presented, right? So we have the fault in horizons here. As you can see in this image here, we have a fault here. So this is the fault that we are talking about, right? So this is the fault in horizons. So with this fault, we can pick this fault and get all the information that we have here. And this is another plane from this fault that we can also here. And also another here is more linked with the horizons here. We are modeling also the horizons here, the base of the reservoir and also the top here. So with the structural modeling, we have the faults, the internal faults, and also the limits. The limits is, or this field here is also limited by faults. So with this information, we have our structural model built for the geological model. So we have the reservoir boundary here, and also the internal faults. So we're also modeling the horizons. We have from the top to the bottom of the reservoir. So we build this structural model. We assign the information that we have from the well logs to this grid that we create here. So phases, I will not give a lot of detail about phase because Manuel already presented this information. So I will pass fast for this information here. So I just would like to see what's happening here when you are relating one well with another, just to give an idea about what's happened when we have the information here. For example, we have this is a sandstone here, and this sandstone just disappeared in this well. What I mean is just disappeared. It's a kind of a pinch out that we have in the model. So this pinch out created here, we need to include this information in the geological model and also further in the reservoir simulation grid. So this porosity, just an explanation about porosity. Manuel already presented this information here. I will pass fast. And also we have the petrophysics and the core analysis here. Permeability, I will give a little explanation about permeability. I will not give details today about this because it was already presented by Manuel. And also here, the core description, porosity, and permeability. This is the core analysis that's used to get from the well log, when we are performing here. So we have here the log and the porosity, the horizontal direction. So with this information, we can correlate porosity and permeability. And the geological grid, this is the geological grid. As I previously presented, this is a high resolution grid. So this high resolution grid is 25 meters by 25 meters by 1 meter. So this is the structural model that we have. So imagine you have plans to simulate this grid using your commercial simulator. It's impossible because this model will take for at least 20 days to simulate about 30 years. So we need to be careful because with this geological grid, it is impossible to simulate for thousands of runs. Right? So with this, we have the structural model and geological grid. So we need to fill this grid with a lot of information, porosity and permeability in all directions. So we have the 3D phase simulation. So we have the inputs, we have upscale well logs, vertical proportion curves, variogram per phases. This information is just to set up your modeling. So we need to have information in order to as much as possible to give the right directions when we are modeling and we are filling this geological grid with all the information that we have. The phase models we use to use the simulation, sequential indicator simulation with vertical trend. This vertical trend that I mentioned here is the vertical proportion curve. So I don't know, maybe Manuel presented this about the phase modeling, about how the simulation indicator sequential use. So maybe you can go there and just review what it means about phase modeling. And we are talking about this algorithm here. We are to fill all the information. And we have also the output here. This is the 3D geological information. So just to remember, we have the well log, the vertical resolution is about 20 centimeters here. And we have the 3D grid, we have the resolution, the vertical resolution is 1 meter. So we need to upscale this information here for the new grid that is the geological grid. So this is we can see here, this is the original well log with this vertical resolution, and this is the resolution of the grid that we built. So when we are talking about a discrete information, we use the most probable phases here. So we can see here, you just include the most frequent information that we have here. So, okay, with the upscale well logs here, we can now simulate. And using this simulation, geologic simulation here, we need to include the information that we have. We are not just simulating, we are including additional information, that is the vertical proportion curve. This is a typical vertical proportion curve that we have. So this vertical proportion curve just gives us an idea about the amount of, in this case, we are talking about phases that you have when you are moving in depth, right? So this is the origin here, 0, and this is the depth of 106 meters. So, and this is the type of phase that we have, phase 0, 1, 2, and 3. So we can see here, phase 3 is most frequent on the base of the reservoir, right? So we have the vertical proportion curve. We also have the variogram. The variogram is just giving us an idea about how is the behavior of the phase when we are moving in the horizontal direction. So this gives us an idea about the vertical direction, and this gives us an idea about the horizontal direction. So with this two information, we can now perform the modeling, the geologic modeling. And this is the one example of the one output after this phase geologic modeling. So we can see here, it's good to remember. This is the information that you have just in the wells. So we need to fill the information the information that is in between the wells. So this is the information that we need to perform this geologic modeling. So this is the information that you have at the top of the reservoir, and this is the base. Just remember, when we have the production, when we observe the vertical production curve, I mentioned about the phase 3 is concentrated on the base of the reservoir, and this is what we are seeing here. So we have the base reservoir, the most frequently, phase 3 is the most frequent one here. And this is another 3D visualization here. This is the top reservoir one side and the other side. Okay, we model the rock types that we got on here, phases, and we are moved to the next one, is the property modeling. Property modeling following the same sequence that we are talking about the phase modeling. So we have the upscale well logs, we also have the variogram here, and we perform a different algorithm because we are talking about now about porosity, and porosity is not a discrete information. So we need to use another algorithm, is a stochastic algorithm. That is the simulation, is a sequential Gaussian simulation. So, and as output, we have the 3D petrophysical information. So this is the result of the property modeling. This is the top reservoir, and this is the base. This property is the porosity. So I will not give you details about the information that you have from well logs and etc., but follow the same sequence. We are just changing the algorithm, and we are changing the distribution of information that I have. Now I'm working with porosity and etc. And this is the permeability. As we observe, the porosity and permeability has this almost the same pattern because they are well correlated when we're talking about the core analysis, because these are more homogeneous reservoir. So after building this, we need to check, okay, I build my geological model, I need to move forward, that is the how to create a simulation grid, but we need to verify and validate this information. For this, we have statistical analysis. We used to have mean and standard deviation. We have histograms, because just remember, we have information from well logs. We build our geological grid. With this geological grid, we fill with all the information that we have, phases and porosity and permeability. And also we need to create a third information, that is the information from the simulation grid. So we can use histograms and also compare the information, well log, geological model, and also simulation model. So this is a good test and good validation to see if we have the same pattern, the same distribution of all the properties. We have porosity, it has also for permeability. When we are talking about porosity, just to remember, porosity is a static information. We use to compare the volume of the cells. So with this information, we can also compare the volume before and after an upscaling procedure, for example. And permeability is not a static one, it's a dynamic one. So we need to check the flow behavior. Just to be careful, when I'm talking about porosity, this is different than permeability. When we are talking about, okay, we need to validate and verify this information. Until now, it's okay. Is everybody is following what we are discussing? So, do you have any questions? If you have, you can stop. I can return and explain, because we are moving now to build our simulation grid. Okay. Yeah. So the next step, okay, I have all this step here performed. I will move to the next one, that is to create a numerical simulation grid. So just remember, when we build the geological grid, we have a resolution of 25 by 25 by 1 meter. We are moved to build the numerical simulation grid. The numerical simulation grid, we have 100 here, meters, 100 meters here, and vertical we have 80 meters here. So this is the resolution that we have, and this is the geo cell size here. So this is 25 by 1 meter. So we build our simulation grid. Now we need to rescale the information. So this is the map of porosity, that we have the distribution of porosity here in all the reservoir. So this is the information building two different models. Two different models, I mean different fidelities. I will give more detail about in the end of this presentation here. And here's the different grid cell resolution. As we can see here and compare, this is the high cell grid resolution here. This is a middle intermediate one, and this is a low grid cell resolution here. You can see here the information is following the same pattern, but we are missing some pattern when we are talking about these upscaling techniques. Okay, just partial remarks until now. We have a traditional procedure to generate simulation model. I present this one, going from well log information, passed through geological and petrophysics modeling, and then we're scaling or upscaling the reservoir property simulation models. We use all the information here from geo and petrophysics information in order to build our reservoir simulation model. Phases, when we are talking about reservoir simulation, we are talking about rock type, porosity, permeability, and also here simulation grid. We have the top, base, limits, and faults. Okay, now we move to the reservoir simulation model. The first question, what is a reservoir simulation model? Reservoir simulation model is a computer program that solves flux and mass equations in porous media with defined initial and contact conditions. Professor Dennis will give more detail when he moved to the more mathematical part of this from this class, right? So the idea is to represent a real physical model into a computational one to be solved by the reservoir numerical simulators. Just to remember, we have a reality, and this reality we don't know, so we don't have control. So when we are building a reservoir simulation model, we are trying to represent this reality that we don't have any idea about this. We just have some wells, and this well just give an idea about the information that we have there, and also we have the 3D seismic and 4D seismic that give an idea about, a general idea about the entire reservoir. So when we are building the reservoir simulation model, it's important to put all the information that we have. So the difference of reservoir simulation compared with other areas of engineering. We have a physical column with uncertainties because, as I said, we don't know the reality. We have the scale because we're talking about a 3D geological model. It's not just a simple scale. We have fluid, we have wells. So everything here requires simplifications because if we don't simplify, it's impossible to solve all the equations that we have when we build our reservoir simulation. So when I talk about the uncertainties and about the simplifications, we are talking about sometimes an error. So this error treatment is also very important. So why do we simulate reservoir models? We simulate the reservoir simulation model in order to predict the future performance of a petroleum field of a wide range of operating conditions and uncertainties. And when we simulate and we predict the futures, this helps us to understand and also answer some questions that we have about the field. And when we are answer some information that we have about the field, we are also taking decisions. So these taking decisions, we need to have a base, and this base is the reservoir simulation model based on the objectives of the companies. So all parties, what I mean is all parties, we are talking about geophysical, geological people that work with this model. So we have the reservoir engineering. So we have all parties, this is an integrated work team. So some examples of objectives that we have. This is the increase recovery factor. This is the most important one. We have to increase the production and profits, and also decrease the water production, risk, and so on. The water production is based on the philosophy of the company or the industry. So we have a lot of objectives that we can decide and move forward, right? So some questions that we can answer using the simulators. What if the reservoir is not behave according to observed data? So this is an important information, because sometimes we build our reservoir simulation models and we have a period of history data, and we are, okay, we have the history data, we have the simulation model, so let's see what's the behavior of this model. And sometimes it's impossible to get the same behavior that we have from the history. So, and this increases our questions, arise our questions. So what we have in this real model that we are not getting into. So this is important information that we can use in the simulator to answer these questions. And also, what type of laboratory data is required to understand rock fluid properties. So we have here two fronts here, rock and fluid, and also the properties related to this information. So another question that simulators can answer is necessary to do physical model study of the reservoir, because traditional the oil companies don't use reservoir simulation model a long time ago, because we don't have these computers, high performance computers. So sometimes it was impossible to simulate this physical model study, right? And also the last information that simulators can answer, from what portion of the reservoir is the production is coming. So it's an important one, because sometimes we have a well, and this well starts to produce a small amount of water. So sometimes you don't want it to produce water, so you didn't expect to produce this water. So this is a question that simulator can help us, because we can build our numerical simulation model, and also can predict and say, okay, this well will start increasing and will explode the amount of water. So we need to see what we can do in order to avoid this production, this water production coming from this well. So now I want to explain how the reservoir simulator is used. So we use to understand the flow and transport in petroleum fields to make decisions. The petroleum field is then described by nonlinear partial different equations at each grid cell that we numerically solve. So this is the real reservoir that we have, the limits of this reservoir. So we build this grid cell, because we need to build for each grid cell here one an equation. We call here just a normal equation. With this equation, we need to link all the different equations here that we have, and I will explain later how we will make this link. Okay. So basically, what we have three principles. So the first one is related to material balancing. Take about the conservation of material. What it means material balance. So we have mass getting to this grid cell and mass getting out of this grid cell. And also we have this mass in, mass out, and means we have the information here. Let's put it here. So we have the mass from one grid cell to another, mass from one grid cell to another. So we are taking the balance when we are talking about this grid cell here, okay? We are just, imagine that we don't have mass getting or getting out from this entire reservoir simulation here. We are just talking about the mass from one block to another. So the mass through the grid cell here. Okay, so we have here this mass getting and get out from a grid cell, and also we have sometimes a source. What it means a source? A source means a well is a producer or an injector. So the producer, we just get the mass out from the reservoir or out from the grid cell, and the mass in, it just includes mass into this grid cell. So this is the difference when we are talking about mass getting into or mass getting out, and also this mass source. I put it here positive, but it depends when we're talking about getting to or getting out is positive or negative, right? And we have a mass still inside this grid cell. When we're talking about reservoir simulation models, or when we're talking about three different fluid phases, we're talking about oil, water, and gas. So just to remember, when we are talking about this, we have an amount of water that is impossible to get out from the reservoir. So we can have this mass is still inside there. So we just need to be careful because this mass accumulate here is just the amount of mass that we have inside this grid cell block that remains inside, right? And okay, we just include this information from one grid cell, and now we are getting information from all the grid cells. So we need to talk about the conservation law, is expressed in terms of flux from two adjacent grid cells here, and also the accumulation of mass that we have inside the volume, and also the source or the sink that we have here, production here or the injection. Okay, so we're talking about the first principle. So let's just resume the equations that we have here. Professor Denz will give details about this when he starts to present about this information. So we have mass in and mass out, mass source, and mass accumulate here. So we are talking about just a single phase. Just remember, we can have three phases: oil, water, and gas. And here, in order to simplify all the information that I'm presenting here, I'm just using a single phase general equation, right? So we have the mass in, the mass out, and mass of the source, and mass that is accumulated inside the grid cell or inside the reservoir numerical model. So just building one equation about this mass in. So this part that is related to the mass that is passing through this grid cell, then the source that I'm calling here the key source. The keys is the flow, and here is the mass that is accumulated here in the cycle. And this is just to remember here, we'll see a lot in details. This is the Darcy velocity here. This is the fluid density. Fluid density multiplied by the porosity here. And this is the key source is the max production or injection per unit of time. So this equation represents the conservation principle in any point of reservoir, just using a single phase. Okay. The second principle is the Darcy law. That is, this Darcy law just deals with the relationship between pressure and fluid flux, right? So we have now the interaction between grid cells. When we are talking about this conservation mass equation, we are talking about the mass just keeps inside the grid cell. Now, okay, we have this grid cell here. We need to quantify the interaction between this grid cell here with this one here with this one, etc. So this is the second principle. So we have this is the generalized Darcy law equations. This generalized Darcy law equation takes into account the permeability, right? And also the fluid viscosity here. And also the gradient of the pressure here. So it's the flow potential. So, and this X here is just the direction that we are talking about. We are talking about the X directions, the Y, or the Z directions. So this is the second principle, Darcy law. So we are moving the fluid between the grid cells. So we need to check how this moves, how we can deal with the pressure and the fluid flux, right? And the third principle is the equation of state, because we are dealing with relationship between fluid densities and pressure. And this is, we must use to, here is the formation volume factor. That is just to have a relationship between the volume that is the subsurface or the volume that is inside the reservoir, the standard conditions here. And also we can relate to the fluid density here. And so this is, we're talking about the first principle, the second one, and the third one. So now we have the three principles. Now we can build our general equation. So our general equation relates all the three principles that we present. So with these general equations, we have here the general equation for the x directions, for the y direction, and the z direction. The fluid here relates to the fluid getting or again out from the grid cell, the key source here, and the accumulated mass here. So we have the relationship now with pressure and time. So this is when we are talking about the pressure and time, this is the general equation that the simulators wants to solving pressure and time. Just remember, here is just one equation for one grid cell, right? So imagine now m cells, so we have m equations. So when we're talking about a simulation grid, for example, with 100,000 grid cells, we're not talking about 100,000 equations to solve. So this is the reason that we're not solving all the equations analytically. We are solving numerically. So this is the reason that we use the Reservoir numerical simulator in order to solve all these equations. So it's impossible to solve analytically. We need to solve a numerical. So just remember, here I'm talking about just one phase. So when we are fancy to use more than one phase, or we are talking about multi-phase flow, so we have this number of equations multiplied by 3. Just remember, 3, oil, water, and gas. So now, so this is the solution. The solution of equation 4 is the major problem of reservoir simulation. So we have all this equation, this general equation, by each grid cell, by each fluid phase. So this is the main problem that we are when we are talking about reservoir simulation model, because we need to consider fluid saturations, we need to consider relative permeability, we need to consider capillary pressure, and etc. Okay, so in resume, what we have a reservoir simulation model divided into a number of cells. That is a space discretization here. We have the grid cell with rock properties, porosity, permeability, relative permeability, and capillary pressure. We have also the geometry. We have the initial fluid distribution. We have the fluid properties, the relation among pressure, volume, and temperature. That is the PBT tables that we use to call this in order to include in our simulator. We have here the well information. We have the production and injection schedule here. And we have also the total time divided in periods of time. There is a time discretization here. Just remember, we build the spatial grid, that is relation between X and Y and Z, and also we need to divide this simulation time that we want to solve all the equations. We need to divide in short periods of time. That is we call this time discretization. So how does the simulator works? So we present the 3 principles. With these 3 principles, we build the general equations for a single phase and also for one grid cell. So now we have this general equation applied for the 3 fluid phase and also for all the grid cells. So how does the simulator works? So first of all, we start with the grid cells having a certain initial saturation and conditions given. This is the contour conditions. Professor Dennis will give more detail when he presents the mathematical developing of all these equations. We define a total simulation time and the time step which it is to calculate. So we have all the equations. Just to remember, these equations we have here the time. So, but we cannot solve this equation for a time of, for example, 30 years. We need to break in a lot of small piece of time here in order to solve all this equation here. So we have this total simulation time. So we define time step in order to calculate all these equations. We calculate or use an assigned production or injection volume. Then the simulator calculate the flow between the grid cells during the time step that we previously defined here, and the new saturation for the grid cell. Just remember, we have initial saturation with this information here. Solving these equations, we have a new saturation for each grid cell. So the reservoir simulator will repeat the process until the desired total time. So we have a lot of small piece of time here, and this is the total time that we have here. This is the initial time, we have the 0 here. So this is the simulator is solving for this time here. Okay, solved is converged, because just remember, we are talking about partial differential equation here. So we are solving this equation numerically. So if this equation converge, including a certain error, okay, we move to the next time. So if converge, okay, move to the next time step. So until we reach the final simulation time here. So this is the process that simulator is using. It's solved for one time step, moving to another, and etc. So the contribution of any reservoir block penetrated by a well to the well flow rate is independent of the flow equation of that block. Such contribution has to be estimated separately and then substitute into the flow equation for the well block that is solved by the simulator. So this is the contribution when we are talking about the reservoir block, when we are talking about when we have a well that is perforated. So we need to include this information separately. Just to remember, when you are talking about this equation separately, you are talking about this term here. And these terms include separately. And how to treat this information separately. So we have the production rate equation for a well block. This is the common equation that we use to. So this is the information that we have in the pressure for the well block, and this is the pressure the well. So pressure well block. This is the geometric factor of the well, right? This is the formation volume factor, and this is the viscosity. So we calculate this separately, and then we include in our equation using all the information that we have. So this is a common problem when we are talking about, okay, when we are talking about different grid cell resolution, we are talking about different geometric factor. Geometric factor means we are talking about different grid cell resolution. So the original well was perforated. We are talking about the flow in porous media. And when we are talking about a grid cell resolution, we are talking about a cell of 100 by 100 by 80 meters, for example. And this geometric factor change. So when we're talking about this production term here that we include in our general equation, we are talking about this four information here that we need to include. So how to represent this information in the simulator? So first of all, we treat it locally independent of the thermal flux, just to remember. So we have three different conditions to operate for a producer, for example. If the well is shut, the equation is 0, right? So if we have the information that is about the production rate, what means the information? Just to remember, we can have history data. So when we have history data, we have this information here. So this equation we have is this key observed here. When we have the information from the pressure, so the information is in the well is this one here. This is the information that we have in the grid block, and this is the information that we have in the grid block in the well. Sorry. So this is a different type that we can have when we are talking about a producer. When this producer is closed, it's 0. When we have this information informed to the simulator, because we have historical data here. So this is information, the observed information. And when we don't have this observed information in terms of production rate, we have this information in terms of bottom hole pressure. So just use this term here as observed. So this is the well representation in a simulator. Moving to the next, the final step when I talk about the reservoir simulation in terms of equation that simulator is solving, it's important to highlight that the production of well is a function of fluid rate and well pressure. So in a history match scenario, we have the oil rate. Well, in this case, oil rate is specified to the simulator. So it starts to operate by this production well constraint in the well. So the other well constraint is not specified. So the well pressure becomes a value to be matched and resume a primary well condition specified and I work in the model to match the other. So this is the information that we are talking about when we have this reservoir simulation model and we have the information from the historical data. So how we use this information in the reservoir simulation model? So we have three conditions. When we form the oil rate, we specify the information as a well constraint. So when this information is not informed, we just solve this information, replace this information by the information that we have. And then we can change this as a primary well conditions and work the model in order to match the other. So when I'm talking about primary condition, because I'm using this information as a primary information in order to solve all the equations. So the reservoir numeric simulator has the information of the well. That is the information that we have. I have here the fluid rates. So the fluid rate from the historical data is in front of the simulator. With this information, I can move to the next step and then use this to solve all the equations that we have. So the partial remark that we have here, we know that reservoir simulation is a widely used technique in petroleum area, and trend of reservoir simulation model is defined toward high complexities. And the main objective when you're talking about a model that needed to be matched and uncertainty that must to be reduced is to understand the flow and the transport in reservoir in order to increase reliability of reservoir prediction to make better decisions. So this is the first part that I talk about how to build reservoir simulation constructor, how to build the reservoir simulations, how the equations is using into the reservoir simulations. All these equations that I present in this section, Professor Denz will give much more details when he presents all the mathematical formulation of this, right? You don't need to be careful when we are talking about these equations. It's just to have a broad idea what how to build reservoir simulation, what the reservoir simulation is trying to solve, and how we are trying to use the reservoir simulation, right? So this is a general idea, and I would like to inform to you guys. So, okay, we're talking about reservoir simulation construction. Now we move to the complexities that we have here. The complexities, I can just pass through what the information that we have. So what we have this one a famous example that was presented in 1969 by Odd. This is a famous model that we call is a tank model. Tank model is a 0D dimension. So we have just here a basic building block of reservoir simulation. The oil remains in place is just the difference of the oil that we have original and the oil that is produced. Okay, it's just a conservation of mass. So when we move to 0D, that is the tank model, to 1D, what we have here? We need to solve all the equations. We have the block that we want to solve the equation, and we have the neighbors. The neighbors that we have here is just on the horizontal direction. Okay, this is the 1D. When we move to 2D, now we have here our block, and we have 4 neighbors. Okay, because we have the neighbor in this direction, the neighbor in these directions here, the neighbor in this direction, the neighbor here. Okay, so we have 4 directions here. When we move to the 3D, that is the most famous grid that we built for reservoir simulation. Now we have direction in 4 directions this, and also the directions in the vertical. Let's see here. I just cut out this here in order to see. Okay, we have the block here. We have these directions, okay, and these directions. So we have the original from the 2D and more 2D extra directions. So with this, we have 6 interactions. So in the 3D, we have 6 interactions. So with these 6 interactions, we need to build the equations. Now we are talking about, okay, we have the directions. So we have now the interactions. We need to build for each grid cell here, 6 interactions. So the material balance of flow equations we need to build for each phase that we can have into the 3 phases, the oil, water, and gas, and the grid block. With the grid block, we have 6 interactions here. So, and also to include the information that you have from permeability, porosity, fluid, and rock properties. This is the variety with grid block and also with time. So, with the traditional mathematical models, we can solve this, okay? But just remember, this we are talking about a regular grid. Regular grid is simple, it's not too complicated to solve just using mathematical formulation. So now we move to the more irregular geometry. So we are not talking about a regular grid, and we increase the number of grid blocks. And also the level of heterogeneity that you have, porosity and permeability. And we are talking about now non-linearity. We are not talking about linearity that is easily solved by the normal mathematical formulations. So with this non-linearity, we are talking about relative permeability curves against saturation, capillary pressures versus saturations, and fluid PVT properties. Pressure is a function of pressure, composition, and also temperature. So now we move to the math formulation to numerical models because we are talking about non-linearity here, okay? So this is when we move to the complexity, we need to use the reservoir simulation in order to solve all the equations numerically because we are talking about the non-linearity. We cannot solve just using traditional mathematical models because complexity increase. As the complexity increase, we need to move forward using a numerical formulation. And numerical formulation here is built as a numerical simulator. And the type of reservoir simulator that we have requires understand these words. So we need to check the information that we have. Based on this, we can build our reservoir simulator and also use the correct one. So just to remember, the model, this is the limit of the reservoir, the grid cell here. We include the information of oil-water contact that we have here. We include information from the geologic model through the upscaling techniques. I'm talking about upscaling techniques because it's the most traditional one. I'm talking about the fluid properties. We must include this information in the reservoir simulation model. We must include rock properties. We must include well facilities here, well information, the location, and the type of well, geometry, and etc., and the facility. And also here, the production curves. Sometimes that I have history data, we must include this historical data also in our reservoir simulation model. And when we have the information from the 4D side, we must include this information too. So, okay, we build our reservoir simulation models, we pass through the complexities that arrays the information that why we must include reservoir simulation in order to solve all the nonlinear equations. Now we move to the model validations. Because when we are talking about to build a reservoir simulation model, we are not just talking about the static one. We need to be careful with the distribution of the properties, the flow behavior, if this flow behavior is following the same original model that we have. The original model means the high fidelity one, okay? So this is the information that we have from the well logs. This is the relative frequency that I have from information. What the information that we have here? Here I'm talking about the porosity, right? And this is the percentage of porosity that I have. This is a normal distribution that is a histogram of porosity. This gray color here is the well logs. So this is the information from the well logs that I have. This is the distribution of porosity, the well logs. And after these well logs, I create my model, that is the upscale model. Just to remember, the grid cell resolution of a well is, in this example, is 20 centimeters, right? When we build our geologic model, we need to upscale or get the information from well log for this grid cell. So we have this a lot of information, but we need to include this information for each grid cell, okay? So this is the upscale information that I have here, from well logs to the grid of the geologic model. And finally, this is the dark color here. I have the porosity distribution in the simulation model. So as you can see here, we are following almost the same pattern after creating this porosity distribution of our model here. So as you can see, our model in terms of static distribution is okay. So we are following the same pattern. So when we are talking about, okay, we have the geologic model, and we must perform upscale technique in order to create a feasible simulation model. So we can have variations. What I mean variation when you are performing the upscaling techniques, we can have different patterns. So when I'm talking about the upscaling validations, we need to validate in terms of volume and also the dynamic one. What I mean dynamic one, I will show in the next slide one example for one producer well. This is what we have here is the water rate, and this is the time. So this is the model that is, I'm considering here the high fidelity one, is the blue circle here, and also the 2D model. The 2D, just remember, is the most simple one that we can have, excluding, of course, the 1D and also the tank model. So as we can see here, just changing the grid cell resolution, we can have different type of flow pattern here. So this is a simple one that I just getting all the information in a 2D, and this is the best information that we can have. It's accurate that we can talk here, the most accurate model, we have a different pattern. So this is the validation that we need to be careful. So it's very important you don't need to simulate all the wells that you have in the reservoir. You can just using one well in order to check and validate the simulation model. So here I'm just giving this example how different the models can be, use different grid cell resolutions, okay, in this simulation model. So this is the type of comparison that we can have, okay. This is in blue is our reference. Our reference means the geologic model, and in red is the simulation model. As we can see here, we have the same pattern but different production curves. This is before before the calibration, okay? And this is after the calibration. So as you can see here, now I have the reference model is the high fidelity model here, is following the same behavior in the same production curves of the simulation model. This is a very good comparison that we can do. We have the simulation model at the geologic scale, we have the simulation model at the simulation scale. So we just include one well and put in this well to produce the oil for a period of time, and then you check the both production curves and compare. Okay, my model is okay or not. If it's not, you can perform analysis and check what's going on. Okay. So, okay, we are talking about the reservoir simulation model. We are talking about the reservoir simulation model validation. So what the information that we must consider when we are talking about validation? The first one is the computational time, because we have a number of cells and also number of time steps. We need to be careful in terms of instability. What I mean is instability. We just remember the reservoir simulator is trying to solve thousands of nonlinear equations. And sometimes we are using a numerical technique, and this numerical technique is just an approximation of the real math formulation, right? And this is not the exact solution. And this is not exact solutions. We have also the physical is not realistic. So if it's not exact solution, we have a problem here. So with this problem here, we have instability in our simulation model. With this instability, we can increase the time to solve all the equations. So we need to be careful with this in terms of computational consideration, right? And also we can have numerical dispersion here from the real field, from the numerical model, because sometimes we have the flow in a porous media, and we are representing this flow in porous media in a grid cell. And when we are talking about the grid cell, we are talking about this. Just to, for example, here I have this grid cell resolution here and here, and this. We have this this 1D just to see about what we are talking about, the numerical dispersion in terms of water. This block has initial water saturation, right? So the flow is in this direction. So we have this block, grid block here, filled with one amount of water, and then with this flow reach this next grid block, we fill with all this information here. For example, let's suppose here, we have 20% of water saturation. We have 20% of water saturation. Here we have 5% of water saturation because the water here doesn't reach this grid block yet, right? And here we have the 5, this is the percentage of oil. So, okay, if we are moving this direction. In this case here, okay, the water reached this block here, so we have 20%. And this block is not already reached, so we have 5 here. So if we look for the same instant here, so the water reached these two grid blocks here at the same time, okay. But when we move to the next one, this is not more 20, not more 5, now it's 20, because the water reached this grid block. And now the grid block is not 5, it's 20, because the water reached this grid cell here. So we have here this block, 20, 5, and 5, and this block is already filled by water. So see, we have when we're talking about the grid resolutions, we can have this kind of dispersion here, and we need to be careful with this, of this water moving from one grid cell to another. And this is very common to happen. So you need to be careful with this. And when, okay, we build our reservoir simulation model, and we need to check the consistency of the numerical solution. How we can do this? We can check the material balance error. This is not guaranteed that everything is fine, but it's the first information that we need to check, and check the number of time step, number of cuts, number of solving iterations. Number of time step, I mean, we are solving all the nonlinear equations. When we are solving these nonlinear equations, what is the number of time step that I can have in order to solve all the equations for the total simulation time. So this number of time step is very good in order to check the consistency of the numerical model. Number of cuts, okay, because when we are talking about solving all the equations numerically, we can not reach the desired tolerance that we define in the numerical simulator. So we need to perform some cuts in order to check, okay, it's not solving the equation with this initial condition. I will give an extra one in order to solve the equations, and then try and check if this numerical model is okay or not. And then the number of solving iterations. Solving iteration is the techniques in order to solve all the nonlinear equations. All this information here that I mentioned is including the numerical simulator output. So you can check all this information here. So, and this information will be very important to know that they exist, and you can check when Professor then presents all the mathematical formulation from this, you have all the information there. So you can ask, and remember here, oh, Professor, I saw this information in the numerical simulator. How we can link this formulation with all this information here. So he will give a lot of details about this, because the simulators include all the information here. And sometimes you see a lot of information and you don't care. So you need to be careful, because your simulation model, you must check the numerical consistency of this. Here is just one example. When we have a bad numerical parameter and we have a good one. Okay, when we are talking about the numerical parameter, I'm talking about I'm solving a lot of equations. So with this, a lot of equations, we need to set up how we want to solve all these numerical equations. So with this information, we can have this numerical parameter that I'm talking about in the simulation. Here is just an example and application when we use a good numerical parameter, and when we use the default numerical parameter in the simulator. So we can see here, this is the elapsed time that we use to build these risk curves. This elapsed time is 20,000 here seconds to build this production risk curve here. And this, with a good numerical parameter here, is the same model, the same parameter input. We use 9,000 seconds. So as you can see here, we have the same behavior, the same curves, the same everything here. We save a computational effort in terms of 47% here. So this is an important thing when we are talking about to build our reservoir simulation model. Not just, okay, I build a reservoir simulation model, I give all the information for us, permeability, oil-water contact, the limits, and etc. Not just this. We need to set up the numerical section in order to have good results. And these numerical sections impacts directly in the total time necessary to run just one single realization. And this I have here 405 samples. Okay, so you can save 47% off. So the bottom lines of reservoir simulation models is a powerful technique, and also this technique validates the effects in petroleum productions. Just remember, where we have the reality, that is our petroleum reservoir. We go through the mathematical formulation, and this mathematical formulation is enough to solve a simple case, simple reservoirs. And when you increase the level of complexity in terms of grid and fluid, etc., we must solve this numerically because it's impossible to solve mathematically, right? And even we have the numerical simulator, is not an easy task because we have high complexity and also high heterogeneities. And just to remember, is a reality that we don't know. So is another point that we need to include. So, and another point is not to build our reservoir simulation model, is also to check if the results is okay or not. Because if the results is not okay, you need to be careful because we are representing a reality, a physics that is not realistic. So just to remember. So we also need to build consistent and efficient reservoir numerical models. This is vital because save long time execution runs, right? So with these reservoir simulation models, we can mitigate risk, uncertainties, and also maximize the return over the long-term times. This is the most important thing. Why we use the reservoir simulator? We use to understand about the reservoir, to increase the reliability of the prediction, and also to maximize return. This is the main objective of our oil company. We need to maximize the profit, maximize the return. And also as times goes on, we needed to understand, to have basic understanding about reservoir modeling, because it's necessary, because you have a reservoir simulation model ready, but if you don't understand the main principles that was used to build this reservoir simulation model, can have a problem in terms of understanding a certain type of flow, a certain type of behavior that is happening and you cannot understand. So it's good to have a basic understanding about reservoir modeling, about your geo model that you have, and etc. And it's very common also for the reservoir and reservoir engineers to set up problems to decide appropriate input data to evaluate the results is a work team here. And also reservoir simulator, as a previous explained, is a set of equations for each grid block. One equation is right for each component or substance compromising the reservoir, comprising the reservoir fluid description. So this gives a general notion about reservoir simulation models, and you need to be careful. You need to pay attention of this. Okay, then I move to the second part that is talking about blocks and emulators. Professor Dennis, can we use to have a break? Or?
Guilherme, yes, you can make a break as you wish.
So everybody is okay if I continue?
Maybe it's a good idea to stop the recording. We can make a break and then you can go to part 2.
Yeah, 5 minutes.
Okay.
So people, 5 minutes of break.